Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
In the annals of 20th century physics, the year 1915 stands as a monumental turning point. It marks the culmination of a decade-long quest to redefine our understanding of gravity, a force that had remained largely unchallenged since Newton's formulation centuries prior. David Hilbert, a mathematician of unparalleled breadth and depth, contributed decisively to this revolution with his work, Foundation of Physics. This work offered not merely a refinement, but a wholesale reconstruction of the very fabric of spacetime. To appreciate Hilbert's contribution, one must first understand the intellectual crisis brewing within the physics community. Newtonian gravity, while successful in describing planetary motion and numerous terrestrial phenomena, exhibited critical shortcomings. It posited instantaneous action at a distance, a concept increasingly incompatible with the emerging principles of special relativity. Furthermore, it struggled to account for anomalies in the orbit of Mercury, a persistent thorn in the side of Newtonian orthodoxy. Albert Einstein, initially grappling with these issues, embarked on a tortuous journey to develop a relativistic theory of gravity. His initial attempts, however, proved fraught with difficulties. He struggled to reconcile the principle of general covariance, the idea that the laws of physics should appear the same in all coordinate systems, with the existing understanding of energy conservation. The path towards a consistent and complete theory remained obscured. Enter David Hilbert. Hilbert possessed a formidable mathematical arsenal, honed through decades of pioneering work in diverse fields, including axiomatic geometry, functional analysis, and number theory. He recognized the profound mathematical challenges inherent in formulating a relativistic theory of gravity. He perceived general relativity not simply as a physical theory, but as a mathematical problem of immense beauty and complexity. Hilbert's engagement with contemporary physics was significantly influenced by figures such as Gustav Mie and his attempt to construct a unified field theory. Hilbert sought a complete set of field equations for gravity, derived from a fundamental principle, an action principle analogous to those used in classical mechanics and electrodynamics. The specific problems that captured Hilbert's attention included, firstly, the requirement of general covariance, ensuring that the laws of physics remained invariant under arbitrary coordinate transformations. Secondly, the vexing issue of energy conservation in a generally covariant theory presented a significant obstacle. Thirdly, elucidating the precise relationship between gravity and the distribution of matter, thereby establishing how matter curves spacetime, formed a crucial component of his endeavour. Hilbert employed invariant theory, a branch of mathematics concerned with identifying quantities that remain unchanged under specific transformations, as a central tool. He further utilized the action principle, which posits that the dynamics of a physical system are governed by the minimization of a certain quantity known as the action. He aimed to construct an action that, when minimized, would yield the field equations governing gravity, much like the Euler-Lagrange equations derive the equations of motion in classical mechanics. The historical circumstances surrounding Hilbert's work are intertwined with Einstein's own struggle to complete general relativity. Both men were deeply engaged in the problem, exchanging letters and ideas. Hilbert's approach, however, differed markedly from Einstein's. He aimed for a more rigorous, axiomatic derivation of the field equations, minimizing reliance on physical intuition and maximizing mathematical precision. Hilbert's proposed action took a specific form, involving an integral over spacetime of a Lagrangian density that included the Ricci scalar, a measure of the curvature of spacetime, and a term representing the contribution of matter. This action, now known as the Einstein-Hilbert action, is the cornerstone of general relativity. Its mathematical derivation involves sophisticated techniques from tensor calculus and Riemannian geometry. The subsequent priority dispute with Einstein over the discovery of the field equations has been a subject of much historical debate. A purely academic perspective focuses on the content of their respective publications. Both men arrived at the same set of field equations independently, utilizing distinct approaches. Einstein relied more heavily on physical reasoning. Hilbert focused on mathematical rigor. Hilbert submitted his work on November 20, 1915, a few days before Einstein submitted his own final version of the field equations. The initial reception of Hilbert's work was somewhat overshadowed by the intense focus on Einstein's theory. Nevertheless, leading physicists and mathematicians of the time swiftly recognized the significance of his contribution. Hilbert's axiomatic approach provided a crucial mathematical foundation for general relativity, solidifying its place as a cornerstone of modern physics. Hilbert sought something more than a phenomenological description. He sought a foundation as solid and undeniable as Euclidean geometry. His work served as critical bedrock. Hilbert's solution to the field equations of general relativity, presented in his 1915 essay The Foundations of Physics, represents a monumental achievement at the intersection of mathematics and physics. His work distinguished itself through its axiomatic approach, deriving the field equations from a variational principle. This contrasts with Einstein's root, which relied more on physical intuition and successive approximations. Hilbert's approach stemmed from his deep understanding of mathematical physics, particularly his expertise in variational calculus. Hilbert's derivation begins with the Einstein-Hilbert action. The Einstein-Hilbert action is a functional of the metric tensor and the Ricci scalar. Explicitly, it takes the form of an integral over spacetime involving the square root of the determinant of the metric tensor multiplied by the Ricci scalar. The Ricci scalar itself is a contraction of the Riemann curvature tensor, a tensor that encodes the curvature of spacetime. To obtain the field equations, Hilbert applied the variational principle to this action. This principle states that the physical laws governing a system correspond to those configurations that render the action stationary, meaning the first variation of the action vanishes for physical configurations. Mathematically, this involves taking the functional derivative of the Einstein-Hilbert action with respect to the metric tensor. This variation yields a complex expression, which, upon simplification, leads to the Einstein field equations. The derivation requires careful handling of tensor calculus and Riemannian geometry. Hilbert demonstrated a mastery of these mathematical tools. The result are field equations with a cosmological constant term. This contrasts with Einstein's early formulation, which initially lacked such a term. Hilbert's derivation established the field equations as a consequence of a well-defined variational principle, providing a solid foundation within established mathematical frameworks. A crucial element of Hilbert's approach involves the concept of coordinate invariance, also known as diffeomorphism invariance. General relativity posits that the laws of physics must be independent of the choice of coordinate system used to describe spacetime. Hilbert recognized that this principle must be explicitly incorporated into the derivation of the field equations. By carefully constructing the Einstein-Hilbert action to be invariant under coordinate transformations, Hilbert ensured that the resulting field equations would also satisfy this fundamental requirement. In mathematical terms, this means that the action remains unchanged when the metric tensor undergoes a transformation induced by a coordinate change. This is achieved by expressing the action in terms of tensors, mathematical objects that transform in a specific manner under coordinate changes. Hilbert offered rigorous proofs and mathematical justifications for his claims. These proofs relied on the machinery of tensor calculus and Riemannian geometry. He demonstrated how the variational principle, when applied to the Einstein-Hilbert action, leads unambiguously to the Einstein field equations. Furthermore, he meticulously addressed potential ambiguities or inconsistencies that could arise during the derivation. His proofs involved detailed calculations with tensors, Christoffel symbols, and the Riemann curvature tensor. Hilbert provided a level of mathematical rigor that greatly enhanced the credibility and acceptance of general relativity. The similarities between Hilbert's and Einstein's derivations of the field equations are striking. Both men arrived at the same set of equations, albeit independently and through distinct methods. The central difference lies in their respective approaches to the problem. Einstein's approach originated from physical considerations. Hilbert's approach started from mathematical principles. Hilbert's derivation offered a more systematic and mathematically rigorous path to its conclusion, while Einstein focused on the physical interpretation of general relativity. Hilbert concentrated on its mathematical structure. Hilbert's work profoundly impacted the development of general relativity. His axiomatic approach and variational formulation provided a powerful framework for further research. The mathematical expertise that Hilbert brought to bear on the problem helped solidify general relativity. It elevated it from a theoretical framework to a mathematically sound theory. The techniques and tools he introduced, such as the Einstein-Hilbert action and the variational principle, became standard in the field. Hilbert's foundational work retains significant relevance in contemporary research. His formulation of general relativity as a variational theory plays a central role in modern attempts to quantize gravity. Approaches such as loop quantum gravity and string theory often rely on variational principles. They seek to formulate a quantum theory of gravity by quantizing an appropriate action functional. Hilbert's work on general relativity serves as a guiding example for constructing these theories. In cosmology, Hilbert's inclusion of the cosmological constant in the field equations is of paramount importance. It provides a theoretical explanation for the accelerated expansion of the universe. Hilbert's formulation of general relativity, derived from the variational principle, underscores his profound mathematical rigor. This has proven instrumental in the progression of general relativity and contemporary theoretical physics. The Einstein-Hilbert action, born from Hilbert's work, has emerged as a pivotal tool in theoretical physics. It remains relevant in areas such as quantum gravity and cosmology. Hilbert's lasting contribution highlights the indispensable role of mathematical precision in unlocking the secrets of the universe.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.